How's everything going? So questions? Smaller class today. ODP 15 is posted, and for 15 you're implementing a subset of a Q package. And all you're making is two functions, well three, there's an init, which just zeroes out the head and the tail, insert, and remove. But remove is a reserved word. If you include stdio, so you got to call it QRemove. And I reposted the assignment a couple of hours ago to note that change. So implement insert and remove. You have a pair of pointers, tail and head, and you have a Q that you can call whatever you want. But just allocate it as an array of 10 integers. And so to insert, you store the thing that you're inserting at Q bracket tail, and then you increment tail. And you got to do it in that order. If you do it in the opposite order, it doesn't assess 100%. To remove, you return the element at Q bracket head, and you increment head. So it's really just storing things and retrieving things in this first in, first out order. That's all you need for ODP 15. And that opened this morning and is due tomorrow morning. ODP 16 is due Friday morning. And it's the same thing, but you actually implement a circular Q. So the only difference is the following. One, when you increment tail or head, if it's equal to 10 after you increment, set it back to 0. So that you can go back and reuse earlier portions of the array. And two, you're going to write an isFull function. And isFull tells you when you have 9 things in this array, basically. So you can do that by counting, but the more general way to do it is if you're going to insert something else, after that insert, you're going to increment the tail. And if incrementing the tail makes it equal to the head, then your Q was full, and you shouldn't have inserted. So your isFull can be as simple as tail plus 1 modulo 10 equals head. Doing modulo 10 just does that rollover for you. So if either tail plus 1 equals head or tail plus 1 equals 10 and your head's equal to 0, those are the two cases where you're full. And then ODP 17, which opens on Friday morning and is due Saturday morning, is just changing from integers to strings. So it's almost exactly the same, except your array, instead of being an integer array, is going to be an array of strings. And you can fix your string length to 120, and your insert takes a string, your remove returns a string. Everything else is the same. So it's like 3 changes to your program. All right, so I'll post details for these as they open tomorrow morning and Friday morning. And if there's questions, go ahead and throw something up on the discussion board. But they should be pretty straightforward to do. And you can use these in your breadth first traversal of your tree for PA4. So we're building up the Q functions. All right. Let's look at how we do the breadth first traversal with a Q. And then I want to go through all the details of deletion from a tree. So let's do BFS first. And the idea is something like this. right? So here's a tree, and a breadth first traversal would want to pick up A, and then B, C, and then D, H, F, and then E, and then G. So move across each level and move down slowly. Okay, the left node, right type traversal we've been doing are depth first. This is a breadth first. And it's a really simple algorithm if you have a queue available. So to do this, we do the following. Insert the root node into the queue. And you're going to want a queue that holds either nodes or pointers to nodes, as opposed to just integers. So however you change it to work with strings, change it again to work with pointers to nodes. So first thing we do is we insert the root node or a pointer to the root node into the queue. And then we just go through a loop while queue is not empty. So temp equals remove. So remove whatever's at the head of the queue, put that in a temporary variable, which I'm calling temp. Print the data for that node. And then insert temp left. If not null, and insert temp right if that's not null. And that's your whole algorithm. And it really is just about 5 6 lines in C. It's not recursive, okay? Most of your routines are going to be recursive. This one's not. This one's just a loop. But it's this simple. So you see the whole process by inserting the root node into the queue. So let's see what this does. Here's our queue. Here's our output. And here's my temporary variable temp. So first thing we do is we insert the root node. That's the letter A, or the node A. So that goes into our queue. And now we run through this loop. The queue's not empty. So remove whatever's at the head of the queue and put that in temp. So I remove this, queue's empty, temp is equal to A. Print out temp's data, so I'm just going to assume these are the data values. So we'll print out an A, and then temp left is not null, it's the node D, so insert that into the queue. Sorry, temp left is B, so insert that into the queue, and temp right is C, and that's not null, so insert that into the queue. Go back to the top of the loop. Queue's not empty, remove the head, that's a B, so our temp is B. Print out that data, which is B. Temp left is now D, right? Temp is right here, so the left child is D, that's not null, so put that in the queue. Temp right is null, so we don't insert that. Go back to the top of the loop. And we just keep doing this. So queue's not empty, we'll remove a C, that becomes temp. We'll print out C. Left child is H, that goes in the queue. Right child is F, that goes in the queue. Top of the loop, remove D. Temp is D. Print it out. Left child is null, nothing to do. Right child is E. Insert that in the queue. And you can see what's happening. We're dealing with everything in the order that we inserted. And each time that we get to a node, we insert the children on the next level. We're not going to deal with those until we're done dealing with everything at this level. So that's where we're getting the breadth first behavior from. So back to the top, pop off the H. Temp is H, nothing on the left, nothing on the right. Output the data. Back to the top, pop off the F. Output the data. Left child is G, that goes in the queue, nothing on the right. Back to the top, pop off the E. Print the data, nothing to the left, nothing to the right. Back to the top, pop off the G. print the data, nothing to the left, nothing to the right. Back to the top, now the queue is empty. And so we're done. And the traversal output was A, B, C, D, H, F, E, G. So that's our breadth first. So pretty straightforward once you have a queue package, okay, which is why you're doing the ODPs ahead of time. So once you've got those, you've got a queue package, you can tell if your queue is empty, right? It is empty function. You have insert and remove, and it codes more or less exactly like this. So any questions on that? All right, let's tackle tree deletion. Have we talked formally about PA4 yet?
Not really, no.
Yeah, because we don't meet on Fridays, we didn't meet on Monday. Let me go over PA4 first. So PA4 is posted on Canvas, and I posted some additional notes this morning to clarify. I got to change my camera angle here. All right, so PA4, you're basically writing a package of functions to interact with binary search trees, and then a main program to drive it and let the user insert things, search for things, and so on. So what I'd like the main program to do is really simple message in the beginning. Just tell them, hit a question mark for help, okay, and wait for a command. So if you want to see the command options, you can do question mark. And there's only a few commands that the system knows about. So we can say delete followed by an integer, and that says remove the node containing that value from the tree. We can say search for an integer. We can type in just an integer without a letter in the beginning, and that means insert that integer into the tree. And then X will examine the tree, will show us the contents of the tree, its depth, its balance factor, a whole bunch of information, which we need to talk about. And question mark will give a help message, and anything else we'll just say, put in a question mark for help. Please don't print the whole menu of options every single time the person types something. Okay, it makes it really difficult to grade. So they type a command, just do what the command says to do, and it's spec'd out in the assignment. Okay, so let's build a tree. Let's build this tree. So I'm going to type a 20. That should insert a 20 into the tree. No messages, it just did it, right? Put in a 10, it put a 10 into the tree. Try to put in a 10 again. Now you can put a message saying error, 10 is already in the tree, because you can only put things in the tree once. Okay, I'll put in a 30. So my tree should look like this. Okay, I can search for 10 and it finds that. I can search for 20, I can search for 30, all of those are in the tree. If I search for anything else, it should say not in the tree.
And so naturally, when it's laying out this tree, it's just going to do less than on the left, like greater than on the right?
Yes, and you're just going to move down until you get to something where there's no child in the direction you need to travel, and you just put your node there. So if I insert a 5, it goes to the left of this node, it goes to the left of this node, there's nothing to the left, that's where the 5 goes.
So it's very possible that when we arrange this data, we happen to start with a low number, that it's going to be a very lopsided tree.
Yes, absolutely.
So,
Okay. That's good.
okay.
Yeah. Right, you do not want to readjust or rebalance your tree. Okay, because I'm going to insert nodes in particular orders, I'm going to look for trees to be built a certain way. And if you're rebalancing it, then your trees aren't going to look like they got built right. And then I got to dig into your code and take a really close look at every single line that you're doing. You don't want that, right? You want to just look at it and say, hey, that looks great. So don't rebalance. All right, so the X command will show you the following information. So it will show you the 3 depth first traversals: pre-order, in order, and post order. And the assignment specifies this format. I'd appreciate your sticking to this format. NLR : comma separated list of nodes. LNR : comma separated list, and so on. So the in order traversal, left node, right, should be in sorted order. The other orders, if you stare at this and you practice traversing in different orders, if we want to do node left, right, we would do a 20, and then a 10, and then a 5, and then a 30. That should be NLR. But it's that second one that really is a quick check, right? Because the numbers should come out in increasing order. And if they don't, it tells you right away that there's an issue. This fourth line, breadth first search, that's the traversal using the queue that we just talked about. And that should ring true really quickly, because 20, 10, 35 is 20, 10, 35. And even if you have a really big tree, if you just read across row by row, that's the order that you should see things in the BFS entry. So that's another quick and dirty check to see if your tree looks reasonable. All right, did we define height? Right, I think we actually wrote some recursive code for height. So height is the depth of the deepest node, where depth is the number of edges from the root to a node. So in this case, the deepest node is right here, 1, 2 edges. So the height of this tree is 2. If I insert the number 12, that should come down right here. It should not change the height. So now if I examine again, the height should still be 2. Okay, so height's another measure you can use to tell if you're doing the right thing. Now if I start inserting a bunch of nodes like 4, 3, 2, 1, well, this is clearly my deepest node, and the number of edges from here to the root is 1, 2, 3, 4, 5, 6. This tree should have a height of 6. So that's what height should tell you. And balance we'll talk about shortly. All right, that's all your program's doing, right? So you can insert nodes by just typing a number. You can search for a number, you can delete a number, you can examine the tree. And Control D will exit, and you don't want any memory leaks. So you want to free all the storage in the tree at the end.
For balance, is it just, it's the whole tree, right? Like,
It's the whole tree.
for like there, it says like 6. Is it that like?
So the height is 6.
The height is 6, but it's, oh wait, can you go up a little more?
Yeah.
So like you had those wait.
So balance is different from height.
Yeah, I know that you're supposed to have like everything filled in for balance. Can
Yeah,
you
basically.
show that tree right there with the height of 2?
Mm-hmm.
Is that, oh never mind. I think it's,
So we had originally this,
Yeah.
right, and that had a height of 2 because this was the deepest node, and then I added another node here.
Uh-huh.
This has a depth of 2, this has a depth of 2,
Yeah.
right? And this has a depth of 1, 1, and 0. So the deepest node is 2, so that's the height of the tree.
Okay, and that'd be balanced, right?
This turns out to be balanced, yes.
Okay, that makes sense.
Yeah. So if we have an empty tree and we examine it, the height is -1, right? That was our weird definition. Null tree is a height of -1. The traversals don't output anything. I should have put it in a new line after my BFS. And it turns out to be balanced. And if we just make a tree with a single node and we examine that, all the traversals just show you that root node, and it has a height of 0.
Okay.
All right, so let's talk about balance. That's pretty useless. All right, formal definition of balance. All right, first notion of a balanced tree is a null tree. If a tree is empty, we say that it's balanced. Okay, it's just by definition. Or, if the tree is not null, we need 3 things to be true for the tree to be balanced. We need the left subtree to be balanced. We need the right subtree to be balanced. And if we look at the height of the left subtree, and we subtract the height of the right subtree, and we take the absolute value of that, it's got to be less than or equal to 1. So an empty tree is balanced. A tree with balanced left and right subchildren with heights that are almost the same is also balanced. So it's a very recursive definition. But it makes it really easy to code also. Right, you can convert this very directly into C code, so we can make a function called balance, takes a tree, returns 1 if it's balanced, 0 if it's not. So if t equals null, return 1. If balanced t left equals 0, return 0, because the left subtree is not balanced. If balanced t arrow right equals 0, then return 0, because the right subtree is not balanced. Otherwise, we know both subtrees are balanced. If absolute value of height t left minus height t right is bigger than 1, return 0, because the heights differ by more than 1. Otherwise, return 1. So pretty straightforward to code recursively. What does this actually mean? So is a null tree balanced? Right, definitely, because that's our first case. How about a tree consisting of a single node? Right, because it's not null, but its left subtree is null, and that's balanced, and its right subtree is null, and that's balanced. And the height of the left subtree being null is -1. The height of the right subtree is -1. -1 minus -1 is 0. Absolute value of 0 is less than 1. So this is balanced. what about this? So is the left subtree balanced? Right, the left subtree is just this, which we already decided was balanced. The right subtree is null, which we also know is balanced. The left subtree is a single node that has a height of 0. The right subtree is null that has a height of -1. 0 minus -1 is 1, less than or equal to 1. This is balanced. And this is certainly going to be balanced because the left and right subtrees are balanced and they both have a height of 0 and their difference in height is less than 1. So this is balanced. What about this? So the left subtree is balanced. The right subtree is balanced. The height of the left subtree is 1. The height of the right subtree is -1. 1 minus -1 is 2. That's bigger. So this is not balanced. But this will be balanced. Because that's balanced, and this is a height of 1, and this has a height of 0, and those differ by only 1, so this is balanced. So what about that? That's also balanced, which doesn't feel quite right. But this has a height of 1, this has a height of 1. This is balanced, this is balanced. So that whole thing is balanced. But if I go on to this, the left and right subtrees have the same height, they both have a height of 2. But this tree by itself is not balanced. So this whole thing is not balanced, even though it looks balanced. Looks like it was balanced. All right, so intuition is usually not too far off, but sometimes, like this one over here, it can fail you. But you can trust the definition.
When I look at it, the easiest way to tell if it's balanced or not is that you filled up the entire level before you move down to the next tier.
Right. What about this? Oh, that's automatically not balanced. We're good. Yeah. I did one the other day and it seemed like it violated that intuition, which is how I like to think of it. So yeah, I think that's good intuition. So yeah, the idea is to fill stuff in up here before you start going deeper. And balanced trees, again, we like the balanced trees just because they minimize the time it takes to operate on these trees. Because usually the time is related to how deep you have to go. And so you fill in your data as much as you can before you increase the depth. All right, so that's the balance notion. And it's a pretty short function to implement for PA4. All right, so let's do tree deletion. And deletion is the hardest part of PA4. There's a lot of pieces of code to write for the whole assignment. You have 3 traversals plus a breadth first traversal, which needs a queue. There's insert, there's search. But those are fairly small pieces, right? Some of them take other pieces and put them together. But the algorithms are pretty straightforward, right? How do you search? Just search left and right subtree. If it's in one of those, then it's in your tree. If not, and it's not the root, then it's not your tree. But deletion is is trickier. So let's code this up. So all of this is going to be based on a struct node star. So remember what our struct node looks like. It's got a left pointer. It's got a data, which for us is usually an integer, but it doesn't have to be. And it's got a right pointer. And let's typedef this. And I'm just going to call this a tree with a big T. That's a pointer to a struct node. So our delete routine is going to take a tree and an integer, and it's going to try to remove the node containing that integer. And the first thing to note, and this is the extra note I posted on Canvas today, is that delete and insert need to return a tree. The reason is we don't have a sentinel node. We added a sentinel node so that we would never change what our list was pointing to. It always pointed to a sentinel. We don't want to do that with trees. We want some variable t of type tree, and if our tree is empty, we want t to just be null. If our tree is not empty, we want t to point to the root. Okay, if our tree is empty to begin with, t is null, and then we insert a node, t has to change. Now it has to point to that node, which means our insert routine needs some way of changing this argument that we pass to it. We pass it a tree pointer, which is null if the tree is empty, and after we call insert, t has to be pointing to this new node. And so our insert routine is going to return the root of the tree. Specifically for that case where we go from an empty tree to a non-empty tree, it'll return the root. Same thing with delete. If t is pointing to a tree and we delete the root of that tree, t's got to point somewhere different now. And so we simply return the root of the tree after we've deleted the node. So return possibly the new root of the tree after deletion of whatever node contained then. All right, there are about 16 million cases for deletion. So we'll spell these out in detail. But again, what I want you to think about here is the algorithm, not the code. I'm going to write some pseudocode, but I don't want you to get focused on the code. Okay, focus on the algorithm, think about the algorithm, ask questions about the algorithm. The code will follow very, very easily from the algorithm. Okay, or if it doesn't follow, we can have a conversation about that, but that has nothing to do with tree deletion. It has to do with pointers and syntax and stars and ampersands and all of that stuff. Okay, well, what I want you to think about here is the algorithm that we're using to delete a node from a tree. Clear? All right, so how do we delete from a tree? Simplest case, we're given an empty tree and asked to delete a node from it. There's nothing to delete, so we just return the argument that we were given, which is null. And to the caller, we handed you a null tree and said delete a node, and you just hand us back a null tree. Okay, that's our base case. If the number that you want to delete is smaller than the root of the tree that you were given, that means it sits somewhere in the left subtree of T. So all we've got to do is call delete and and say delete n from the left subtree. And as long as we believe delete works correctly, this will remove n from the left subtree and it will return a pointer to that left subtree with the deleted node. And we need to put that into the tree as the new left subtree. So here's our original tree. And here's T. And we're deleting something smaller than A. So we know it's somewhere over here. We call delete, we hand it this tree, and the node we want to delete. It removes that node. And delete returns the pointer to this left subtree. And now we just say T arrow left equals whatever that subtree is. The reason we have to do that is because suppose we were deleting the node B, our delete routine would be asked to delete the root of this tree. It will change the root to some other node, and we need to make sure that when we come back from deleting from that left subtree, that A is pointing to the correct node on the left. Or in the extreme case, where your tree looks like this, and we call our delete routine to say delete X from T, and X is less than A, so it will call delete on this subtree. And when delete removes X from this subtree, it's just going to return a null. And we need to change this to point to null now. If we don't do that, it's still going to point to that node X, which we probably freed in our delete, and now it's pointing to random stuff. So this removes a node from the left subtree, takes that new tree with the node deleted, and makes that left subtree of T, our original tree. And then we ourselves have to return the root of this new tree, which is just T. Because we didn't change the root, we just changed stuff to the left of it. And the same thing happens if n is bigger than T arrow data. T arrow right equals delete. T arrow right comma n, and then return T. So we have three cases on the board. Tree is empty, nothing to do. Tree is not equal to the root. It's smaller than the root or it's bigger than the root. We just call delete recursively. Take the return from delete and use that as the new left or right subtree of the root. Questions on those? Because I'm going to erase this, so we're going to go deeper. All right. So the last case is deleting the root. So we want to delete the root of T. About anything on the right, because we're not going to touch the right side of the tree. We're going to leave that unchanged. What we're going to do is find the largest node in the left subtree, make that the new root, delete it from the left subtree. And don't just copy the data portion. We want to actually take a node and make it the root. We don't want to just copy its data, because imagine that the data is actually some big, huge, monolithic linked list where each node points to a hash table, where the entries of the hash table are binary search trees, right? And you don't want to copy all that data from one node to another. We just want to move the pointers around. So we want to delete the root of this tree t. And there's about 14 million cases for this. There's actually only 3 or 4. So the first case is there is no left subtree. If there's no left subtree, how can we find the largest thing in the left subtree? So if t left is null, so there's no left subtree. Well, we can find the largest thing on the right and replace the root with that, but we're going to do something even easier. We're just going to move the root of our tree to right here. So how are we going to do that? Temp equals t arrow right. Let me not call it temp, let me call it new root. So I'm going to point new root right here. And then I'm going to free t. And then I'm going to return new root. And that'll take care of that case. So if we're deleting the root of the tree and there's nothing on the left, all we have to do is move the root down one spot to whatever the right child of the root is. The traversal order of this will be exactly the same as it was, except when we traverse the tree, we just won't show the root node anymore because it's been deleted. So to do that, just put a temporary variable to point to the right child, free this node, and then return this as the root of the tree. Implementation, the order is important. What's wrong with this? Once you free t, you cannot access t arrow right reliably. The moment you free t, the thing that it was pointing to might get used for something else. That's what freeing does. It says make this memory available for other applications. And even though the next thing I do is I try to access the right child of t, t could have changed in between there. And now t arrow right might be something totally different from this, and I'd be returning some random root to my tree.
I run into this a lot in object-oriented programming too, like C#. And I often wonder if there's an easier way to do it because, like, I'll have to check, like in this example, before trying to call t arrow right, check is t null or does
Yes.
t exist, and then if t exists, then check where it's right.
Right.
That kind of thing.
Yeah.
And, like, you can't assume it exists when you ask for it, and let alone its dependencies.
Right. Except that we know that t is not null because we already took care of that case in the very beginning. T arrow right is perfectly valid to work with. Right? So I can do this, and if t arrow right is null, this just says new root is null.
Right.
Frees t and it returns null. That's exactly what it should do. So we won't actually get an exception there. But at some point we needed to make sure t was not null before we started dereferencing the fields in t.
Okay.
Right? So yeah, there is that check you need to do, and I think that's pretty much unavoidable. I mean, it seems to pop up every time you deal with either objects or pointers. You just need to know if it's null, or go crazy with your try-catch blocks, or let the exceptions fly. So don't do this, right? For me, when you free something, think of that thing you're freeing as being set to null. Okay, it doesn't actually set it to null, but imagine after you call free that the thing you freed is now equal to null. And then see if your code makes sense. So imagine that free t causes t to be null. This would throw an exception, right? And now I'm trying to dereference null. I'll get a seg fault. So be careful with the order. Temporary variables are your friend when you're doing all this stuff.
That's one more question. When checking to see if it's null, like say up there at the top, if TR right is null, or TR left is null, I've seen it sometimes where people use that as a Boolean, just say if TRO left. Like, as long as that returns something that isn't null, will that go through? And then if it
That's
goes,
dangerous.
it is dangerous?
That works because null is 0. And in C, if you say if such and such, as long as that's non-zero, it's considered true. But what if we were using our PA1 system where null was -1? Then saying if TRO left, that would evaluate to -1, which would be true, right? So you're kind of dependent on the fact that null is 0.
So it's an unsafe assumption.
It's an unsafe assumption, yeah. It's as unsafe as just using 0 instead of null in your code, right? Because that's usually, I've never encountered a system where null was not 0, but we just use null instead. And it's fewer lines of code, but it's no quicker to do it like this as opposed to just if value. All right, so this deletes the root of the tree in the case where there's no left subtree. All right. Next case, there is a left subtree. You want to do a 5-minute break? This is going to get really thick after this. Let's do a 5-minute break. Come back at 5 of.